If F is a field and Px be a irreducible polynomial over F, or Px belongs to Fx, then there exists a extension field K of F such that K is residue classes of I in Fx, where I is ideal of Fx. Since Fx is a principal ideal domain, and from the criteria of quotient ring, quotient ring to be a field if I is maximal ideal of Fx and Fx and I is generated by the Px. Then if Px is irreducible polynomial, then I is the maximal ideal of Fx. Now second thing is Kf. Kf is dimension of K. Dimension of K over F. This is equal to degree of Px. If K is field extension of F, then K is vector space over F. So we define the dimension of K over F. Now third is Px belongs to Fx has a root in K. Now this have some deductions. So now deduction number 1, this is corollary is if Px be polynomial, maybe irreducible polynomial or maybe reducible polynomial over F, or Px belongs to Fx, then there exists a extension field K of F, of field F. Second, Kf is the degree of K over F, because K is a vector space over F, less than degree of Px. And third one is Px has a root in K. Now proof is Px is irreducible polynomial. And has a degree n such that Px is Gx Qx, where Gx is irreducible polynomial of Fx. So extension field K is Fx by I, the residue classes of I in Fx, and I is generated by the Gx, and because degree of Gx is less than degree of Px, so Kf is degree of Px. Now third, Px has a root in K, because Px is Gx Qx, so Pa is Ga Qa, and Ga is 0, because Ga is an irreducible polynomial. So from the previous statement, this has a root in K, so Ga is equal to 0. So this implies that Pa is equal to 0, because Ga is a irreducible polynomial, because Ga is irreducible polynomial. So Ga has a root Gx is an irreducible polynomial, so Gx has a root in K, so Ga is equal to 0. So this Pa is equal to 0, it means Px has a root in K, hence proof.